This video lecture, I am going to answer 10 questions from sample paper number 4, RK Bali Navigation book. This is the 4th edition book. If you have any other edition book like the 5th edition or the 6th edition, no problem, the questions will still remain the same. So let's start with question number 21. In my previous video lectures, I have solved the first 20 questions. Now we will start from question 21. For takeoff, aircraft requires a headwind component of at least 10 knots, crosswind limit of 35 knots. The angle between wind direction and runway is 60 degrees. Calculate minimum and maximum allowable wind speed. So we have been given in the question the minimum headwind component that we must have in order for takeoff and maximum crosswind limit. And we have to find the corresponding wind speeds which will give us this minimum headwind component and maximum crosswind component. So for headwind component, the formula is a long track. Headwind component is a long track component which is equal to minus. Now here minus sign stands for the headwind, wind speed into cos theta. Now the headwind component that we need is a minimum of 10 knots. A minimum of 10 knots. Wind speed, that is what we have to find out, and theta. Theta is the angle between wind direction and runway direction. So that is 60 degree. So cos 60. Therefore, wind speed will be 10 divided by cos 60. Now, cos 10 divided by cos 60 is 20. So minus 20. Here minus stands for headwind component. So you can ignore that. So wind speed is 20 knots. So you require 20 knots of wind speed in order to get a 10 knot of headwind component. Now second part of the question, we have to find crosswind. Now the crosswind component equal to wind speed into sine of theta. So the maximum crosswind component is 35 knots. Wind speed is what we have to find out, and sine theta is sine 60, where theta is the angle between wind speed and runway. So wind speed will be 35 divided by sine 60. So 35 divided by sine 60 is 40.4 or approximately 40 knots. So you need 40 knots of wind speed in order to get a maximum of 35 knots crosswind component. Simple. So correct answer here will be 20 and 40, option alpha. Very simple but very important sum. Next, very important, when climbing through an isothermal layer at constant calibrated airspeed, what will happen to Mach number? What will happen to true airspeed? Okay, so isothermal layer. Isothermal layer is an atmospheric layer of constant temperature. Now, according to ISA, as we climb to higher and higher altitudes, our atmospheric temperature must decrease. It must become lower and lower. But in an isothermal layer, even if you climb to higher altitudes, the temperature is going to remain constant. Okay, it won't decrease, it won't increase, it will remain constant. So, and you are climbing at constant calibrated airspeed. So let's say this is that isothermal layer. Okay, isothermal layer, and you are climbing in this isothermal layer at constant calibrated airspeed. Constant calibrated airspeed. Correct? So what will happen? What will happen to Mach number? Now when you climb at constant calibrated airspeed, your true airspeed of your aircraft, the real airspeed of your aircraft must increase. Why? Now calibrated airspeed is nothing but proportional to dynamic pressure. Now dynamic pressure is part of atmospheric pressure. Okay, is part of atmospheric pressure. Now when we climb to higher and higher altitudes, okay, climbing to higher altitudes, we enter parts of atmosphere where becomes atmospheric pressure becomes lower and lower, right? So as we keep climbing to higher and higher altitudes, atmospheric pressure starts decreasing. So when atmospheric pressure starts decreasing, whatever pitot pressure and static pressure registered by the airspeed indicator will also start decreasing in value. And when this pressure component start decrease in value and the registration is also decreasing, the airspeed shown to us, the indicated airspeed shown to us, or indicated airspeed or calibrated airspeed shown to us will also decrease in value. The aircraft may be flying at a constant true airspeed or at a very fast true airspeed, but nevertheless, the calibrated airspeed, indicated airspeed shown to us will decrease in value. That doesn't mean your aircraft speed is decreasing. It may be flying at a constant true airspeed, but still calibrated airspeed or indicated airspeed shown to us decreases because the pressure that the airspeed indicator registers, okay, or evaluates is decreasing as you're climbing to higher altitudes. So in order to have a constant calibrated airspeed indication, or in order to have a progressive intact calibrated airspeed indication, your true airspeed of aircraft must increase. So in order to have a constant calibrated airspeed indication, the true airspeed of aircraft must increase. When aircraft's true airspeed increases, what happens? Dynamic pressure, which is nothing but impact pressure, dynamic pressure generated at the pitot tube also increases. Also increases. This increase in dynamic pressure, or this increment is necessary compensate compensate for lower atmospheric pressures encountered at high altitudes. At high altitudes. Okay. So when you're climbing at a constant calibrated airspeed indication as given in the question, true airspeed of your aircraft, the true airspeed will increase. The true airspeed will increase. You will have to add more power, increase true airspeed of your aircraft. Now what happens to Mach number? So option C is wrong. True airspeed should not decrease, it should increase. Now option A, Mach number increases. Option B, Mach number decreases. Let's say isothermal isothermal layer is. So this is an isothermal layer. The temperature of this isothermal layer is 30 degrees Celsius. 30 degrees Celsius. 30 degrees Celsius is nothing but 303 Kelvin. 303 Kelvin. Okay. So let's say your initial initial true airspeed of aircraft is climbing from this level to a higher level. Okay. So at this level, let's say 10,000 feet, the calibrated airspeed of your aircraft is 200 knots, okay, at 10,000 feet. Outside temperature 30 degrees Celsius. Now it climbs to a higher altitude of, let's say, 20,000 feet. Calibrated airspeed constant 200 knots. We will check what is a true airspeed. True airspeed should increase. Now we will find true airspeed at 10,000 feet with calibrated airspeed of 200 knots, temperature 30 and pressure altitude 10,000 feet. So I'll show you. Feet with a calibrated airspeed of 2,200 knots, your true airspeed is around 250. Okay, I have not used calculator. This may not be the correct accurate value, but just for understanding, I am taking this value. Now, when we climb to a higher altitude of 20,000 feet, calibrated airspeed 200 knots, the true airspeed should increase in order to maintain a constant calibrated airspeed indication. Your true airspeed must increase. So, true airspeed, let's say, becomes 300 knots. From 250 knots, it has become 300 knots. Now, what will happen to Mach number? Your Mach number is nothing but true airspeed divided by local speed of sound. Correct? Local speed of sound is 39.17 square root of temperature in Kelvin. So 39.17 square root of temperature in Kelvin 303. So local speed of sound will be square root of 303 multiplied by 39.17, which is 681.8 or 682 knots. Local speed of sound is 682 knots. So local speed of sound 682 knots is constant. Even if you are at 10,000 feet, it is same value. You go to 20,000 feet, local speed of sound is still the same. What will happen to Mach number? Now initially at 10,000 feet, the Mach number will be 250 TAS divided by 682 local speed of sound. When you go to 20,000 feet, Mach number will be 300 knots TAS divided by 682 local speed of sound. So 250 divided by 682 is 0.36 Mach number, and over here 300 divided by 682 Mach number becomes 0.44. So actually when you climb from 10,000 feet to 20,000 feet, Mach number increases from 0.36 to a new value 0.44. So correct answer here will be Mach number increases. Next, when descending through an isothermal layer at constant Mach number. Now the same isothermal layer, now instead of climbing, you're descending. So you're descending from, let's say, 20,000 feet to a new altitude of 10,000 feet at constant Mach number. Okay, now you're coming down at constant Mach number. What will happen to true airspeed? True airspeed should increase, it should decrease, it should remain constant. So let's say this is that isothermal layer, constant isothermal layer. You're descending from a height of altitude of 20,000 feet. Okay, a new to a altitude below you, which is 10,000 feet. So let's say again, let's take the temperature to be constant 303 Kelvin. Okay, at 20,000 feet, let's say your Mach number was 0.5. When you come down to 10,000 feet, your Mach number is still going to remain the same 0.5. Now, local speed of sound will be 682, the same as this one. With this temperature 303 Kelvin, local speed of sound is going to remain constant 682 knots. Okay, whether you are at 20,000 feet or whether you come down to 10,000 feet. So local speed of sound you have got Mach number. Now let's calculate TAS. TAS is Mach number multiplied by local speed of sound. Correct? What is Mach number at 20,000 feet? It is 0.5. What is local speed of sound at 20,000 feet? It is 682. Now 0.5 multiplied by 682 is 341. So TAS at 20,000 feet is 341 knots. Now when you come down or you descend to a new pressure altitude of 10,000 feet, Your Mach number is 0.5. Local speed of sound is also going to remain the same because we are coming down in an isothermal layer. So your task will be Mach multiplied by local speed of sound, 0.5 multiplied by 682. So 0.5 multiplied by 682 again is 341. So correct answer will be task remains constant. 20,000 feet 341. 10,000 feet again 341. So task remains constant. Question 24. When climbing at a constant Mach number below the tropopause. So in this question, 23rd, you were descending at constant Mach number. Now in this question, you are climbing at constant Mach number, but in ISA atmosphere. That means this atmospheric layer is not isothermal. It is an inversion layer. It's a normal ISA atmospheric layer. What will happen to calibrated airspeed? Very simple question. So the logic remains the same. Whether you are climbing in an isothermal layer, in an inversion layer, or in an ISA atmospheric layer, when you climb to higher and higher altitudes, your atmospheric pressure decreases. And calibrated airspeed indication, okay, this indication is nothing but your indicated airspeed indication. And indicated airspeed corrected for position error becomes a calibrated airspeed. So this calibrated airspeed indication by your airspeed indicator depends on dynamic pressure. Whatever pitot pressure sensed by pitot tube. Now pitot pressure is a combination of dynamic and static pressure. And in addition to this, static pressure is also separately given as an input to the airspeed indicator. The resultant output of all this, that of pitot pressure and a separate static pressure, is that you are left with dynamic pressure. This dynamic pressure is nothing but the speed of your aircraft, proportional to the speed of your aircraft. Now, when you climb to higher and higher altitudes, atmospheric pressure surrounding you decreases in value. When this atmospheric pressure starts decreasing in value, the dynamic pressure sensed by these pressure instruments, airspeed indicator, altimeter, will also decrease in value. Now, if dynamic pressure decreases in value, the airspeed indication will be much less than expectations. Okay, you may be flying at 200 knots calibrated airspeed, let's say, but the indication given to you will be much less than that, because in order to get that accurate, correct indication, you should be having, or you should be able to register, the airspeed indicator should be able to register sufficient dynamic pressure proportional to that speed. But if pressure surrounding your aircraft is much less, you cannot register enough sufficient atmospheric pressure to give that indication speed. That's why when you are climbing at higher and higher altitudes, calibrated airspeed indication automatically decreases. You may be flying at a constant speed, at a much faster speed than that, but indication shown to you will be much less than the actual speed you are flying at. Okay, so this is very important. So question number 24, when climbing at a constant Mach number below tropopause in ISA, calibrated airspeed will decrease. Irrespective of temperature, surrounding temperatures, your calibrated airspeed is only dependent on atmospheric pressure. So decrease. Question 25. In a steady climb with auto throttle maintains a constant calibrated airspeed and total temperature also remains constant, what will happen to Mach number? Now this question is similar to question number 22, which was you're climbing at constant calibrated airspeed, and here it was mentioned that you're climbing in an isothermal layer. Now in this new question, that is question number 25, again you're climbing at constant calibrated airspeed and temperature remains constant. That means indirectly they are trying to tell you you're flying in an isothermal layer. So in that case, what will happen to Mach number? So the explanation remains the same. Look at question number 22 explanation. Mach number increases 0.36 to a new Mach number 0.44. So question number 25 answer will be the same. The logic, the explanation will be the same as question 22. The Mach number should increase, should remain constant, should decrease if temperature is lower than standard. So correct answer is option alpha. Mach number will increase. How will CAS, calibrated airspeed, respond if temperature increases by 5 degrees Celsius when flying at a constant indicated Mach number at flight level 290. That means your aircraft is flying at a constant flight level 29,000 feet. And when you fly at this constant flight level 29,000 feet, you are entering from a cold air mass to a new air mass which is 5 degrees Celsius warmer. Okay, so I'm going to draw that. So this is a cold air mass, let's say, and next to it I'm going to draw a warm air mass. Now let's say cold air mass is 25 degrees Celsius. Warm air mass is 5 degrees Celsius warmer than this. So let's say 30 degrees Celsius. Your aircraft is flying at constant altitude, which is 29,000 feet in both air masses. So over here 29,000, same here 29,000. Okay. And what will happen to calibrated airspeed if you encounter these conditions? Now, one is a colder air mass and one is a warmer air mass, correct? So now in colder air mass, local speed of sound will be different. In warm air mass, local speed of sound will be different. Okay, so let's say local speed of sound in warm air mass is 25 degrees Celsius. 25 plus 273 is 298 Kelvin. Okay, so local speed of sound formula is 39.17 square root of temperature in Kelvin. So 39.17 square root of 298. Square root of 298 multiplied by 39.17 is 676 knots. So local speed of sound in cold temperature is 676. In warm temperature it will be 681.8, that is 682 knots. So in warm temperatures, local speed of sound is always more than cold temperatures because local speed of sound is directly proportional to temperature. Let's say your true airspeed of aircraft is the same. 500 knots, true airspeed 500 knots. Okay. So what will be the Mach number? Mach number is true airspeed divided by local speed of sound. So true airspeed 500 divided by 676 and Mach number 500 divided by 682. So 500 divided by 676 is 0.74. So in cold air mass your Mach number is 0.74. When you enter a warm air mass your Mach number becomes 500 divided by 682, which is 0.73. So with respect to this particular situation, when you are climbing at constant altitude and you enter a different air mass from a cold air mass to a warm air mass, so what happens to your Mach number? Mach number more or less remains the same, 0.73, 0.74. Your task, you're not making any changes to your auto throttle or power. So true airspeed is going to remain the same, 500, 500. Local speed of sound is going to change because it changes with temperatures. Now the last quantity, calibrated airspeed. The calibrated airspeed will remain approximately constant, option Charlie. Like I have said previously, the calibrated airspeed only depends on atmospheric pressure. Okay, disregard the temperature surrounding your aircraft. If you are flying at same altitude 29,000 feet, atmospheric pressure is also going to remain the same, okay, or more or less constant. So calibrated airspeed will also remain the same. Question number 27. If ambient temperature increases by 10 degrees Celsius, okay, that means outside temperature increases by 10 degrees Celsius for aircraft flying at constant TAS, what will happen to indicated Mach number and true Mach number? Okay, so look here. So this question, I can explain the answer of this question with the same logic. Your aircraft is flying at same altitude, okay, as given in the question, and same task. So TAS 500, TAS 500, but it enters a warmer air mass. It enters a warmer air mass, an air mass warmer by 10 degrees Celsius. So here I have taken an air mass which is warmer by 5 degrees Celsius. So let's make it 35. And we have been asked what will happen to Mach number. What will happen to Mach number? Now with a temperature of 35 degrees Celsius, your Kelvin temperature will be 308. It will be 308. 308 square root of that is so and so multiplied by 39.17. You get a local speed of sound of 687 knots. So Mach number will be 500 divided by 687, which is 0.727. Okay, so approximately 0.73, or let's say 0.72. So now what has happened? Your Mach number has decreased from 0.74 to a lower value of 0.72, 0.73. Okay, more or less same, but still it has decreased by 0.01, 0.01, right? 0.74 has become 0.73 or 0.72. So correct answer is, if temperature increases, means it becomes warmer, aircraft flying at constant TAS, your indicated Mach number will decrease and true Mach number will also decrease. So your instrument will show you a decrease in value, and the indication shown to you, the decrease shown to you will be the correct decrease, will be the correct indication. Question 28. Distance is given to you. Outbound speed, homebound speeds are given to you. The time from departure to the point of equal time is what? So we are going to directly use the formula. Distance to point of equal time or critical point is total distance multiplied by homebound speed divided by outbound plus homebound. So 2600 multiplied by 480 divided by 480 plus 395 is how much? 480 plus 395 is 875. 1600 multiplied by 480 is 1248000 divided by 875 is 1426 nautical miles. So distance to point of equal time is 1426 nautical miles. Time to critical point will be distance to critical point divided by outbound speed. 1426 divided by 395. So which is 3 hours 36 minutes. That is equal to 216 or approximately 217 minutes. Next, question 29. Distance, outbound speed, homebound speed, endurance given to you. What is distance to the point of safe return? So again, distance to point of no return is endurance into outbound into homebound divided by outbound plus homebound. So 9 hours multiplied by 465 multiplied by 385 divided by 465 plus 385. 465 plus 385 is 850. 9 into 465 into 385 is 1611225. So distance to PNR will be that divided by 850, which is 1895. 1895. Option C. Question 30. The empty mass of an aeroplane is 44,800, meaning basic empty mass is 44,800. Operational items including crew is 1060, are 2300 kg. So variable load is 2300. Now when you add variable load to basic empty mass, you get 44,800 plus 2,300, 47,100. Next, zero fuel mass is given. What is traffic load? Now, dry operating mass plus traffic load, okay, is equal to zero fuel mass. So traffic load will be zero fuel mass minus DOM. So 65,500 minus 47,100, 18,400. So correct answer is option Bravo. So this concludes our lecture. I hope you have understood all the 10 questions, explanations that I gave. If you have any doubt or any comment, feedback, let me know in the comment box of this video. In my next video lecture, I will be solving the next questions. Keep practicing. Do watch all my lectures, especially now I have uploaded many of them. You can check the playlist and you can find the particular video that you are in need of, and you will find that one. Thank you for your time. Share this channel with all your friends, this particular video with all your friends who are also preparing for the exam. Hit the like button if you have liked this video lecture and subscribe if you haven't yet.